Hello. Today we will talk again about the temDM MSA package and highlight some features that make it different from the other software on multivariate statistical analysis. I should stress it's not just a PCA program. It allows some manipulation in the so-called latent factor space. Actually, these features are already a long time present in the temDM MSA package, but in the new version 2.0, they are significantly enhanced. Well, today I loaded the advanced version. It's a bit different from the basic one. Actually, many features are available in the basic version, but I would like to show you also something special which is only available in the advanced version. Well, we will need the group MSA factor space, and we choose first of all the endmembers tool. Also, we will need our standard learning example with simulated Hills data cube. It's already MSA container prepared, and I assume the sufficient number of PCA components are already extracted. Okay. So what I mean factor space? It's just data distribution plotted in the PCA coordinates. And we can look through that using, for instance, view results tool. Look at scatter distribution between first two PCA coordinates and maybe request third versus second coordinate or some coordinates of higher order. Okay, this way we have a look inside the multidimensional space. Well, that was the view results tool, but we can do much more with the endmembers tool. What is endmembers? Just a set of few simple spectra extracted from your data. They are supposed to have a simple physical meaning. And what is important, it should be possible to represent reasonably the whole your data set as a linear combination of these few simple spectra. Well, how to find them? Let's design a new endmember set by clicking the button New. The scatter plot of major principal components appears, and there are a couple of colored markers there. We can drag these markers along the scatter plot and see live how the corresponding spectrum changes. Well, now our task is to characterize the data variation in this set. It seems to me that there are two major data variation trends. One trend is here and another trend is here. So let's capture that. From the very name, endmember, it sounds that we have to place the marker somewhere at the ends of our variations. So let's put the red marker here, control the corresponding red spectrum. We can play a little bit with the position of the marker, like that is good. And the same we do with the green marker. Well, now I believe we captured that variation trend, but not this one. And to do that, two endmembers is not sufficient. We have to add the third one by clicking the button Add Member. So you see right now we have three endmembers, and new marker, blue marker appears, and the corresponding blue spectrum. So again, we put this blue marker at the end of the second variation trend and optimize a little bit its position. So I believe right now we have designed a good endmember set consisting of three endmembers. We can look deeper into the location of our end members in the multidimensional vector space. Let's add another scatter plot. Scatter plot of third versus second principal component. Just click Add, and here we have extra scatter plot. You see third component is added. I mean, in this particular case, it probably doesn't make much sense because all meaningful variations can be described in this plane, which corresponds to this line in this second scatter plot. But still we have a third dimension, and in principle we can drag our markers into this third dimension and see what happens. But right now we don't need that. It's just to show you this option. We close this scatter plot and look into another option. You probably notice that this end-membering process generates a lot of windows. So many that it's not easy to manage the allocation in the working space. There is some option helping you. You can move your spectra windows anywhere where you want into the working space, but important is the location of the first spectrum and the last spectrum. You should place that manually, and all intermediate spectra, in this case it's one green spectrum, could be automatically placed in a cascade manner in between these two extreme sandwiching windows. Let's do that by clicking this icon. Okay, first, second, third. We can try again, move like that, and click. It's ordered in the meaningful manner. Now it's interesting to see how the found end members are distributed along the dataset. Let's generate maps of end members. Just click Make Maps. Here we are. This window we don't need. It's just repetition of the end member spectra. Close it. And this is end member maps. Right now the map of the first end member is displayed. We can scroll through that by using the standard slice tool. This is the map of the second end member and third end member. So quite reasonable maps. Now we are sure that the designed end member set is good. We can store it. Just press Store and everything is stored in the MSA container. So now we can safely close it, press Close, and confirm. We are sure that we store it, nothing will be lost. Okay, all windows disappear at once. That's very convenient at the end of end-membering design because you generate actually a lot of windows. But we can anytime load them, press Tune Alt, and they are there. Okay, close again. By the way, you can anytime load also the generated maps by clicking Load Alt. Yeah, it doesn't allow you to tune further the end members, but it output the resulted maps and spectra. Then I'm going to show you the automatic procedure of finding end members. We start end membering process again by clicking New. Well, now system recognizes that they are already stored end members in this container, but we want to design from scratch. Press OK. The new end members template is prepared, but now we are not going to move these markers manually. Instead, we go to Auto Finding End Members box and press Find. Well, the system asks you how many meaningful principal components they are. In case this data cube was already denoised by PCA, this number is known and automatically inserted in the box. In case you did not do denoising, you have to decide about that right now and press confirm. Well, in this particular case, we know that they are two principal component, meaningful components. Just press confirm. Then the system is doing some calculations. And after a while, new question. Well, it's long to explain, just empirically. System generates some kind of histogram, and we need the first maximum in this histogram. Usually it's determined quite accurately automatically, but you have to control that. And if the system did some mistake, you have to drag this position of maximum just manually. Then press confirm. Well, new endmembers are ready. You see that these endmembers are very close to what we found manually, but actually the procedure is still not finished. You see that this waiting icon is still working. Well, the system outputs to you just what it considers to be the most probable endmembers. But you have to decide further yourself. Please note this graph in the left upper corner. This is some kind of probability of existing endmembers. And most probably is just this 3, but you still can try to increase the number of endmembers just by clicking this button, right? And you see that a new endmember appears. If we click again to the right, maybe endmember number 5 is there. Please note that the spectra of endmembers are automatically refreshed and order it in the cascade manner. Well, but I think in this case endmembers number 5 and 4 are not very relevant, and you see the probability is not so high. So I suggest to return back to 3 endmembers, just pressing this button, 4, 3, and then press fix. So I think 3 endmembers is quite good for this system. What is important to mention? This automatically found endmembers you can further tune manually just by dragging these markers. And probably it's good to look at more scatter plots. Input 3 here and generate scatter plot third versus second principal component. Well, in this case, it's relatively simple because we can fully understand the geometry of this data set by looking at only 2 scatter plots. But in real cases, it could be more complicated because of many dimensions. And then we can face the following problem. We move, for instance, green marker here, but we have little idea how it looks in another dimensions because we cannot plot all combination of scatter plots. Suppose, just for learning purpose, that in these scatter plots there are some invisible dimensions which we see only during this lesson, and we move green marker here, but we have little idea how it looks in invisible dimension. Maybe it's completely at crazy position, like we did intentionally here. It's shifted to the third component quite crazy. So what to do? There is an extra semi-automatic tool to solve the problem. So you put it to the right position in visible dimension and press fit 1. Up, in invisible dimension, it jumps to more or less reasonable position. Well, that was a semi-automatic tune of one given endmember, but we can also try to tune them all together. Let's again design some crazy configuration and press fit all. You see that all these three end members align to some kind of line, and this is an iterative procedure. We can press that several times and observe that the orientation of that line would slowly approach the direction of the second principal component. And that is the correct result because there are only two meaningful principal components in the system. I call this method also semi-automatic tune because the results are dependent on the initial conditions. Well, you might argue that in this case we actually do not need any automatic or semi-automatic tune of end members. It's much easier to set all end members manually. And you are exactly right. But that is just a learning example, simplified example. In the real spectrum images, it could be much more dimensions, and there you cannot manage end members manually. You need some automatic tools. Let's look at that. Close this simplified example. I open the real life example. That is some semiconductor device examined by ILS. And we start endmembering process. We start from scratch. Template is prepared and we click find. Well, this data cube was already denoised with PCA, denoised with 7 principal components. That's why 7 is automatically inserted in this box. We have just press confirm. Well, system is doing something. In fact, it extracts all possible potential positions of end members in multidimensional space. And in this case, it takes time because there are 7 dimensions, quite a lot. But now we come to the next step, position of the first maximum. I'm pretty sure it's automatically determined good. Just press confirm. And after a while, we have 8 end members. Let's try to determine whether it's optimal configuration or not. Yeah, all markers look quite reasonable, except of this green marker. So let's try to play with number of end members. I think this end member number 8. I have doubts about that. So let's investigate another scatter plots. Scatter plot 3 versus 2. And I guess this end member on the question is here. I think also in this scatter plot it's not very relevant. Let's even look at deeper scatter plots. Well, where is it? Play again. Aha, it was here. So my conclusion is that the end member number 8 is actually not needed. So we can live quite happily with 7 end members. Well, let's fix it. Good. We can check also the spectra of end members. Yeah, for that we need to extend a little bit scale. And we see that the spectra fit pretty good to what we expect a priori for this device. Okay, that was basically all I wanted to show you today. Then goodbye and all the best.